So in this video, we're going to start talking about electrochemistry. So what is electrochemistry? It's the study of the relationship between chemical change and electrical work. Okay? And so electrochemical cells are systems that use oxidation reduction reactions to produce or utilize electrical energy. Okay, so there's two types of cells. There's a voltaic cell where we use a spontaneous oxidation reduction reaction, or redox for short, to produce electricity. It's also called a galvanic cell. And an electrolytic cell is electricity where electricity is used to cause oxidation reduction reaction to take place. Okay, so now you might recall from Chemistry 1 that an oxidation reduction reaction is one that involves the transfer of electrons from one chemical species to another. Okay, and what is electricity but a flow of electrons? So electrochemistry and oxidation reduction are inseparable because electrochemical reactions are redox reactions. Okay, so in the voltaic cell, we're using a redox reaction to produce electricity. So here we have a redox reaction. By definition, it involves the transfer of electrons, and we're forcing that transfer of electrons to take place through our external circuit. So voltaic cell is basically it's a battery. Okay, that's how a battery works. A battery is a harnessed oxidation reduction reaction. And an electrolytic cell is where we use electricity to, drive a non-spontaneous reaction. So that's the opposite process. Okay? So let's talk about some general concepts here. First of all, what's oxidation and what's reduction? This should be a review. All right, so oxidation and reduction always occur together. Why that is, I'm going to talk about. Okay, so oxidation, the definition of oxidation is the loss of electrons or an increase in oxidation number. Okay, so for example, if you go from an iron 2 to an iron 3, and the process involves the loss of electrons, so therefore defines it as an oxidation. Now for monatomic ions like this, we can think of the charge as the same, the oxidation number is the same as the charge. So here the oxidation number is 2 plus, here it's 3 plus. Okay. And what do we teach you all the way back in Chem 1? That positive ions are formed by the loss of electrons. Okay. For example, we could write another reaction. Let's say I'll give you an even simpler reaction. A sodium atom becoming a sodium ion and giving up its electrons, right? We teach you all the way back in Chem 1, one of the early Chem 1 lectures, that positive ions are formed by the loss of electrons, right? Yeah, in an atom you have your protons are positively charged, the electrons are negatively charged in the atom. The two are equal to one another. Okay, how do you form a positive ion? By taking out an electron. Well, that's the definition of oxidation, loss of an electron. Okay, so the opposite of this is the gain of electrons, which is a decrease in oxidation number. So for example, if we have the opposite process, calcium 2 plus ion picking up 2 electrons and becoming calcium metal, that's the reverse process. Here we have electrons consumed. Okay. Here we have electrons liberated. And the oxidation, electrons are on the right side, and the reduction, electrons are on the left side. Now, matter has to balance, even down to the level of electrons. And when we get to balancing redox reactions, the first thing you have to do, you have to balance both the charge and the mass, but you balance the charge first, okay? And that's because the electrons have to balance. If we have some reduction reaction that's consuming electrons, where are those electrons coming from? They're not coming out of a black hole. They're coming from some oxidation reaction. So you can't have a reduction without an oxidation. So a redox reaction is there's always an oxidation. It's a combination of an oxidation and a reduction. Because one more time, the electrons that are being consumed in a reduction reaction are being liberated in an oxidation. So the reducing agent is the substance that is itself oxidized. So the substance that's oxidized is what allows the reduction to take place. Because as the substance is oxidized, the electrons are given up and they're consumed by the reduction. And the oxidizing agent is the substance that is reduced. Okay? So let's talk about some rules for assigning oxidation number. And let me back up for a minute before we get into this. What do we want to assign oxidation number? Now, it ought to be easy to see why this is an oxidation. An anion becomes a positively charged ion. That's loss of electrons. But what if I gave you something like this? What if I said that sulfur dioxide becoming sulfur trioxide? What if I said that involves oxidation of the sulfur? And you're going to say, how is that? There's no change and the charge is present. Okay. Once we get past monatomic ions and into molecules, you have to be able to assign oxidation numbers to see whether or not oxidation or reduction are taking place. So you have to be able to assign oxidation numbers. It kind of gives you, the oxidation numbers give you a way to keep track of electrons in a molecule. Okay? So, first of all, so what are some rules for assigning oxidation numbers? First of all, any element in its elemental form has an oxidation state of 0. Okay? So how are you going to know? How are you going to know what constitutes elemental form? If it's not part of a compound and it doesn't carry a charge. So for example, sodium all by itself, and it doesn't have a charge, and it's not part of a compound that's elemental form. Na plus is not elemental form because it carries a charge. And NaCl is not elemental form for sodium because it's part of a compound. Okay? Now, those elements that occur as diatomic molecules, H2, N2, O2, F2, and so on, now that's considered to be elemental form. That's the one case where a molecule is considered to be elemental form because those elements occur as molecules. So H2 is hydrogen in elemental form. Okay. So for a monatomic ion, rule number 2, for a monatomic ion, the oxidation state is equal to the charge on the ion. Okay. For example, so for Na plus, the oxidation state is +1. For iron 2 plus, oxidation state is +2. For iron 3 plus, the oxidation state is +3, and so on. Okay? Now, fluorine in its compounds always has an oxidation state of -1. Okay? There's very few things that we can teach you in chemistry without having to also teach an exception. There's no exceptions to this rule. In a compound, now I'm not talking about elemental form, I'm talking about in a compound as fluorine combined with something else. Fluorine will always have an oxidation state of -1. Okay? Oxygen is nearly always minus 2 and 99.9% of your examples out there. The only exceptions being if it's a peroxide, which is O2 2 minus, or a superoxide, which is O2 minus, or if it's combined with fluorine. Okay. Now, hydrogen's either going to be plus 1 or minus 1. Hydrogen is almost always plus 1 unless it's combined with a metal where it has an oxidation state of minus 1. Let's put it this way. It's usually plus 1 with non-metals and minus 1 with metals. So, for example, if you have H2O or NH3 or HF or HCl, all that is hydrogen plus 1, okay, because it's hydrogen combined with non-metals. On the other hand, if you have NaH or CaH2, that's hydrogen combined with a metal, now the hydrogen is going to be minus 1. Okay, those are, by the way, are called hydrides. Okay. Now, nitrogen is all over the place. It can go from minus 3 in a compound like NH3 all the way up to plus 5 when paired with oxygen, for example, and nitrate. Halides are also all over the place. They can go from minus 1 all the way up to plus 7. Minus 1 paired with members lower in the group, and plus 7 paired with members higher in the group or with oxygen. Okay, and so the last rule here is that, and this is important, is that the sum of the oxidation states is going to equal the charge on the molecule. Sum of the oxidation states has to equal the charge. All right, so let's look at some examples. All right, so let's look at nitrogen and nitrite. Nitrite ion is NO2 minus. So we have a nitrogen and we have 2 oxygens. And we know the oxidation numbers have to add up to minus 1, not minus 2, minus 1. Right, because it's an NO2 minus, it's a minus 1 ion. So if each oxygen is minus 2, okay, what's the nitrogen going to have to be to make all that add up to minus 1? You know you're dealing with nitrogen plus 3. Plus 3 minus 4 is minus 1. Okay. Now if we move up to nitrate, which is NO3 minus, now we have a nitrogen and we have 3 oxygens, but all that still has to add up to minus 1 because it's still a minus 1 ion. So if each oxygen is minus 2, okay, now the nitrogen is what? It's plus 5, right? Because plus 5 minus 6 adds up to minus 1. Okay? Now, one more example here. What about chlorine and ClF3? Okay, so we have a chlorine and we have 3 fluorines, and all this has to add up to 0. Well, how do I know it has to add up to 0? I don't see a charge here. It's not ClF3 plus or ClF3 minus. There's no charge on that. Okay, no charge on that, so it has to add up to 0. Well, one of our rules said fluorine is always minus 1. So to make all that add up to minus 1, the chlorine has to be what? Plus 3. Okay. And then last, what about, let's see, nitrogen and the ammonium ion? Well, we know hydrogen I'm not going to draw this one out, but we know the hydrogen is always +1 when compared with, or when combined with nonmetals. So if hydrogen is 4 hydrogens would be +4, so therefore the nitrogen would have to be -3. In other words, -3 plus 4 adds up to the charge, which is +1. Now let me show you a couple of more quick examples here. What if you had something like, let's say, oxalate? You might not ever have heard of that ion before. That's the oxalate ion. Okay, now let's figure out the oxidation number of the carbon. Okay, now I picked this for a reason. So you have 2 carbons. So we have 2 carbons. And 4 oxygens, and that has to add up to -2. Okay, that has to add up to -2. So if each oxygen is -2, right, that's -8. So the carbons have to be +6, but there's 2 of them. So each carbon is +3, right? Because +6 minus 8 makes 2 minus, okay? Or similarly, if you look at something like dichromate, okay, that's dichromate. So we have chromium, 2 chromiums, and now we have a whole lot of oxygens. We have 7 of them. Right? But it all still has to add up to -2. Right? So if each oxygen is -2, well, all this is going to add up to +14. Right? So each chromium, the chromium is going to have 2 minus, so the 2 chromiums together are going to have to be +12, but there's 2 of them, so each chromium is +6. So +12 minus 14 makes the 2 minus charge. Okay? So all other things being equal, you should be able to see this now. Okay? All other things being equal, any reaction which increases the number of oxygen atoms around a central atom is an oxidation. Okay? Now what do I mean by all things being equal? I mean the same central atom and the same charge. Okay? So for example, if we go from nitrite to nitrate, we have the same central atom, which is nitrogen, and both are -1 ions, right? So this constitutes oxidation of the nitrogen. If you work it out, we did work it out a couple slides ago. So that's oxidation of nitrogen from +3 to +5, okay? Or if you go sulfite to sulfate, okay, same thing, same central atom, same charge, that's oxidation of sulfur from +4 to +6, okay? Or what about chlorate to perchlorate, that's oxidation of chlorine from +5 to +7, okay? Now, what about this example I gave back at the start of the video? I said, what if I told you sulfur dioxide to sulfur trioxide constitutes oxidation of sulfur? Now you can see why that is. in the sulfur dioxide, we have sulfur and we have 2 oxygens, and it all has to add up to 0. I don't see a charge here. It's not SO2 plus or SO2 minus. It's just SO2. So if each oxygen is minus 2, then what is the sulfur? Sulfur is plus 4. All right, which if we come over here to the sulfur trioxide, now we have 3 oxygens, but it still has to add up to 0. As you see where I'm going with this. You're probably skipping ahead in your right now in your mind. So what's the sulfur now? It's plus 6. So what are we doing? We're basically oxidizing the sulfur from plus 4 to plus 6. So this ultimately where this is coming from is the way electrons are shared in a covalent molecule. For example, when you do formal charge, you divide the electrons equally. When you do oxidation, you assign the electrons to the more electronegative element. That's where all this is coming from. You're describing the way electrons are shared, ultimately, without having to go to all the trouble of drawing out a dot structure. Anyway, we'll talk about that. And we're going to talk about balancing redox equations in the next video.